Okay, hi everybody, welcome back to the Geotechnics Lab. Angus here again, and we're going to look at consolidating our sample in this video. So, let's start with the Geotechnical Modelling board that I've drawn up here. So for consolidation, this graph in front of us is the fundamental thing we need to consider when we're planning out our consolidation and using the pressure flows from the cell pressure and the back pressure controlled by the controlling software to create our test plan. So, returning to our graph of voids content or specific volume against a log of P dash, we're going to think about a few different things. The first of which is our pre-consolidation stress, marked out here at the top of this curve. Before we move to pre-consolidation stress, we are on what would be a kappa line of sorts, and we want to move past that fairly swiftly. We're not really concerned about the behaviour on this line, mainly due to the fact that the way we created the samples wasn't in isotropic compression. It was in one-dimensional consolidation, if you think back to one-dimensional compression theory. So thinking in terms of our CAM clay frameworks, we have a slightly different QP space with one-dimensional compression as we do in isotropic compression. So we want to move past this point fairly quickly and move on to our lambda line in isotropic compression. So although we think, or we can estimate our pre-consolidation stress of around 50 kilopascals that we're at already, we do want to move fairly quickly past this point. So I'm going to assume, for the sake of argument, that our pre-consolidation stress, once we get past 150, we know for sure that we are on our lambda line. So that's going to be the first point that we move in our P dash. I know Charlie's talking about some of this in some of the videos that he's producing for the geotechnical modelling side of things, Dr Heron that is. But for us, we just want to move past that point fairly quickly. So 150 kilopascals on the P dash line is a number that we want to get to fairly quickly. After that, we're going to get a couple of readings along our lambda line before we move up our kappa line. So I'm going to set the stresses to go to 150, 300, 450. So we arrive at the point here, and then we're going to move back down a kappa line to 350 and 250 being our bottom stress on our kappa line, and then we're going to move back up our kappa line with an increment to 400, and then we return to the lambda line at 500. So on this kappa line we have a good what would that be? 4 readings on our kappa line. That should be enough to plot a nice line down there, and perhaps if one of the points came out slightly erroneous, or it would give us a good line of best fit to draw down our kappa line. So then we can estimate our kappa value for this soil. Obviously half of it is kaolin, as I've mentioned in previous videos, and we roughly know the value of kappa for kaolin. We can then have a look at how that compares when we add 50% of a sand silty sand of 600 micron. After we've gone off our kappa line, we get 2 more readings of 500 and then 700, where 700 is our new P0 dash. P0 dash, of course, being the maximum isotropic stress that the sample has experienced, or the maximum stress. And so in that 700 we have, hopefully, and there is a few bits of research conducted into this, we've hopefully completely destroyed the 1D-ness or the one-dimensionality of our compression in our QP space. This is a question for Professor McDowell and the other lecturers on the module, but when you're considering your QP space, you need to consider what framework you're actually in. One-dimensional compression, modified cam clay, normal cam clay. There are a few others of the QP bulb that you can draw. And at 700 kilopascals, certainly for a sample that was only ever compressed up to 50 kilopascals of pre-consolidation stress, you hope that by that point you've completely destroyed the one-dimensionality and you know for sure that you're in QP space. That's crucial when you come to the shearing. And our shearing stress for this course, for this testing framework, pretty much following the standard coursework that's given out to fourth year and master students here in previous years, where we're using an over-consolidation ratio of 1.2. So I'm dividing 700 by 1.2 to get this final P' value of 584, which is my over-consolidation stress. I've indicated that on this plot here by P' final, P' fin. So now we need to, once we've come up with our test plan and we have an idea of the different values we're going to get, we know that we've got enough values to plot our lambda line and our kappa line. We could even get a small kappa line from here from 700 to 584 kilopascals and give a judge of how that lines up with our kappa line before. But now we need to think in terms of practicalities. How are we going to get our values of P' in our cell? So one thing we need to think about is the back pressure. We'll start with that first. Now, we've used the back pressure before when we were thinking about saturation and our B check. We closed off different valves and such. The main thing to consider here in consolidation is that you can't really decrease your back pressure. Otherwise, you will be drawing air that might be in your sample out of solution. That returns back to the stuff we talked about with saturation and flushing. So there are two things you can do. You can either keep the back pressure the same, or you can increase your back pressure, further compressing the air within your sample and forcing it into the water solution. For our purposes, we are controlled, or we are limited by the ability of the controllers, the stress controllers, the pressure controllers. We have a maximum pressure on both controllers of 1,000 kilopascals. So if we want to arrive at a pressure or a P' of 700, and we have a back pressure currently set at 300 that we set previously when we were doing our B check and doing our saturation, we are pushing the limit there of our pressure controllers. So we can't really increase our back pressure here and force more water out of the solution. So we're going to keep our back pressure all the same. So let me mark that on the board now. Okay, shoddily drawn, but you get the idea. We're going to keep our back pressure throughout the consolidation stages at 300 kilopascals. So now we need to calculate quickly what our cell pressures will be to arrive at our values of P'. So let's mark that in now. Again, here I'm doing, as before, P' is cell pressure minus back pressure. Okay, so now we have our cell pressures. We know what cell pressure we need to set throughout our consolidation to change the P' value within our sample. So now let's take a look at our controller, because that's where we need to set these values. So we'll start here. Okay, is this recording? It's recording. So returning to sort of the familiar window for our pressure controller here, we have a field in the consolidation area, in the consolidation tab, talking about cell pressure. Now, again, it varies by application to application. However, we know that the cell pressure is the thing we're going to change. So in this software, we have the option to change cell pressure. So I've already gone in and I've set our cell pressures like we have on the board there. We've got 450, 600 and so on our consolidation cell pressures. Now there's one thing we haven't considered just yet, and that is how long we're going to leave each consolidation stage for. Now in the standards, it talks about moving on to the next stage of consolidation when you have a small change in the volume of water inside your sample over a very long time. So let's talk briefly about that and explain what that means. So just to start with, we know from our E log P dash plot that the voids content, or the specific volume of our sample, is changing as we change our stress. It's either decreasing or increasing along the kappa line and then decreasing again. What does that look like in our sample? We have the back pressure controller line here, and we have the cell pressure controller line. The cell pressure is going to increase. Now, with the pressure staying the same in our sample that's sealed by the O-rings and the membrane that we looked over in the first video, the water within that sample is going to flow out of these lines in double drainage back into our pressure controller. So at the moment we have a volume in here of 135 cc. That over time through this test is going to increase. Water is going to flow out of our sample and into the pressure controller. Returning back to the theory, we can draw a quick consolidation plot for this. This is showing for a given isotropic stress, increment of isotropic stress, what happens to the volume over time. The volume of the sample, that is. We have this initial volume and we finally get down to a final volume, VF, at time in theory, T100. Now realistically, that time for T100 tends towards infinity. As the volume approaches the final volume, VF, for any stage of consolidation, the time for a small change in volume tends to infinity. It becomes more and more difficult for a given stress to pull water out of the sample, change the volume of the sample. So one way you could tell the controller to move to the next stage of consolidation is to say, well, okay, when this time period gets sufficiently big to make a small change in volume, at that point we know we are pretty close to T100. You know, as you move to 99, 99.5%, 100% consolidation, you must know that you're pretty much there, as that is asymptotic. So then you can say, oh, okay, we are roughly near T100, so then we can move to the next stage. Or you could estimate what T100 is if you have a lot of experience with a certain type of soil, and then just move it on to the next one. Move it on to the next stage of consolidation. That's not technically allowed within the standards, the international standards for triaxial testing of the strength of soils. However, for our purposes, it works pretty well. We know from last year's experience that T100, or the time where we have very small volume changes, approaches 9 hours. And that was with a pure kaolin sample. For our purposes, where we have sand in the mix, salty sand in the mix, we're going to reduce that to 5 hours. So, looking back to our controller software again, in the fields here where we have wait at least minutes for a change of millimeters cubed, that's what we're talking about when we are thinking in the standards of wait for 300 minutes or 5 hours for a change of 1 millimeter cubed. If within 5 hours 1 millimeter cube change doesn't happen, the next stage of consolidation will occur. Failing that, we've also got this box here that says change after 300 minutes. So there's two options for our software there. We've given it two options. If the volume changes of our sample are within 300 minutes become sufficiently small, smaller than 1 millimeter cube, then you can move to the next stage of consolidation, because at that point you have finished that stage of consolidation effectively. It will take very, very, very long amounts of time to get to that T100, to the real T100. Or we say after 5 hours, move on anyway. So there we have it. We have 5 hours to change this sample, to increment our consolidation stress. And this is a pretty simple process within this application. All I have here is start auto cons, automatic consolidation. And once I press that, our sample starts to consolidate, and hopefully it will become smaller as the voids, or the voids content becomes smaller, the specific volume becomes smaller, and water flows out of our sample. So by the time is 12 o'clock on Wednesday morning, by 6 AM on Friday, we should have finished our consolidation, and we should be at a final P dash of 584 kilopascals. So let's start that now. And we should see, if I change my acquisition loop down to 1 second, the sample there has increased its pressure, the cell pressure has increased, the pore pressures have increased, the back pressure has stayed down.
Okay, as I'm editing this back, you might have realised, and I realised, that I've just become quite confused, and I just want to talk briefly about the reason for that. There's nothing wrong with what happened, but the increase in back pressure caught me slightly off guard. The software is clever enough to know that when you increase your consolidation pressure, you want the change in P dash to be almost instantaneous. You don't want it to ramp up over time as the cell pressure increases. So what happens is the cell pressure and the back pressure increase at the same rate until the cell pressure reaches its specified value, or the required value, and then once that happens, the back pressure will drop almost instantaneously to give the correct value, or the correct new value of P dash. So that change in P dash is very quick and over a very short space of time. The software caught me off guard. I didn't remember the fact that happened, but it worked just fine, and I talk about this in a bit when we're looking at the results. So I just wanted to clarify that.
That has increased slightly, and then over time we will see our sample start to consolidate. So Friday we'll see you back here, and we'll have a look at how our sample, how the data's turned out, and we'll take a look at the data over that time. So I'll see you on Friday. Okay, welcome back. It's Friday afternoon. The samples been consolidating over the past 2 days. So let's take a look at how we've got on and look at some of our data and see if we've got a good consolidation phase. So we left on Friday with the sample consolidating, and by the end of the consolidation phase we wanted a P dash of 584, represented by a cell pressure of 884 and a back pressure of 300. Let's just check that we have those values on our pressure controllers, and you can see there we have 883 and 300 on our cell and back pressure controllers. So we are happy that we're at our final pressure. So let's take a look and see if we have got our sample consolidated all the way throughout. It's worth commenting as well on the sample. If you look at the sample, you can see it has shrunk compared to, if you compare a frame from the previous video or the previous part of the video and now, it's definitely shrunk, and you can even see sort of the pore stone there, where it's been set slightly off center from the middle of the sample, or at least the sample has shrunk inside of the diameter of the pore stone. Obviously the pore stone less compressible than the soil. So that's one indication that there's been some consolidation. So what I'm going to do now is walk you through some of the data. This is the Excel sheet. I've made a copy of it, and this is the Excel sheet of the data presented from the controllers. And what I've got up here on the screen, just to show you what's gone on, is the cell pressure and the back pressure over the course of the different phases up to now. So this is right back from when we were controlling the cell pressure and the back pressure when we were doing saturation and B checking and things. So just analysing this briefly, if you look at the cell pressure there, we've got our increases and our decreases and a subsequent increase again, and the final decrease back down to a pressure of 884. So that's good. We've definitely had the cell pressure change. The back pressure as well has these. On the whole, it's a straight line at 300 kilopascals. However, there are these occasional shots up and down in back pressure. And you might ask yourself, well, why has that happened? Well, when the controller software is smart enough to know that when the pressure needs to change for consolidation to set an effective P dash, the controlling software knows that you want P dash to stay the same, or at least rise instantaneously. So what these back pressure increases and decreases represent are the controller trying to keep a P dash constant during the different phases. And I think Dr. Heron or Charlie talks about this during some of his lectures, so I'll save the detailed explanation here as to what exactly goes on with P dash during these cycles. But let's take a look more specifically at the consolidation phase. So what I'm going to do here is delete these graphs, and I'm going to just briefly walk you through some of the data. Now, normally, there are other ways of doing this. You might like to use MATLAB. I've been using Python a lot recently, so a Jupyter notebook or something like that would be very useful for this. But let's just look at the software, the data in Excel. So what I'm going to do here is I'm going to filter the data just to draw out the consolidation phase. So I'm going to set a filter on the cell pressure side of greater than 450 or 445. This number representing the cell pressure when we had a P dash of 150. So that was the start of our consolidation phase. So now we've got this plot. I now want to plot the change in back volume against time. So this is obviously a time series data. What I'm going to do is just insert a scatter graph of all of our back volume data. When the computer works. So this is our plot of the back volume against time. Now remember that the back volume here doesn't represent the volume of the sample. What it reflects is the volume of the water within this reservoir. So at the moment it's 142 cc's. In the controller it's in millimeters cubed. So when we undergo consolidation, we've forced water out of our sample and into the pressure controller. So that's why our back volume has increased rather than decrease as you would think it should do during consolidation. The back volume is the amount of water in the pressure controller rather than the soil. So one easy thing to do here is just to flip this scale and view it in reverse order, and then you can get an idea. So instead of thinking in terms of what's happened to the back pressure controller, you think of what's happened to the soil. So this is water flows out of the soil, and we have phases here representing each phase of consolidation. We have subsequent decreases along our lambda line, some increases in volume in our kappa line, and subsequent decreases again, and then decreases down our lambda line again, and then a short increase in volume as we get to our final over consolidation ratio. And the cool thing about this is you can already tell here the emergence of the lambda lines and the kappa lines. The volume changes, flicking back to our framework again, the volume changes for an equivalent change in P dash or confining pressure. The volume changes are greater along the lambda line than they are along the kappa line because of the smaller gradient. And here you can see that where we are losing volume in our sample down a lambda line, the volume changes in the kappa line, where there is some swelling and recompression, are a lot smaller than they are in the lambda line. So that's good. It shows that we have an emergence of the type of behavior we'd expect to see from what we know of can clay. So that's good. I could also plot from this P dash. So what I'm going to do here is I'm going to scroll back to the top, and I'm going to put another line in. So I'm just going to call this log P dash, and I'm going to calculate the natural logarithm of the cell pressure minus the back pressure. Again, this only works because it's isotropic consolidation. If I was plotting this type of data during the shearing phase, I'd have to use another formula, one that I'm sure you'd be able to work out if you reference either the data booklet, if you are a University of Nottingham student, or if you aren't, you can find this sort of framework, or the CAM clay framework and the formulas associated with it elsewhere. So now I've got log of P dash, I'm going to insert a plot of blank plot. I'm going to select data, I'm going to add a series, doesn't need a name, of log of P dash against the back volume, just to show you some description of volume against log of P dash. And we can see here we get this funny looking graph. Again, we need to flip the y-axis as it is showing not the sample volume but the back pressure controller volume. So we flip that, and I'm going to change the bounds on the y-axis as well, on the x-axis even, to make it a little easier to view. So I'm going to set that to 4.5. And there you can see we have a graph that is similar, although it looks very different, to our theoretical framework where we should have the lambda and the kappa lines. This is the variation in volume, raw volume, so not specific volume. The volume here is dimensional, obviously, in millimeters cubed, specific volume non-dimensional. You could take the correct values from this to plot your lambda and your kappa lines, which is what you'll need to do for the consolidation phase on your coursework, or if you were doing the coursework for geotechnical modelling, or if you're just plotting the behaviour, if you're doing some soil testing, you wanted to see how your consolidation behaviour looks, and start to think of your material properties of lambda and kappa. You could plot them using a graph like this. If you were to do a bit more processing on the data, get the specific volume right, and plot the specific points for the specific P dash at close to T100 for each of these lines. Obviously this is showing you the consolidation behavior over each successive increase in stress or decrease in stress, but that looks broadly similar. You can see we've got some unloading and reloading. Even looks like there's some hysteresis in there, and subsequent final unloading of our sample. So that's good. We have some nice consolidation behavior, and now we can look at shearing our sample. So in the next phase, we need to, now we're at the correct P dash for our over-consolidation pressure, we need to think about doing an undrained shear test. And to do that, we need to come up with a shear rate. Just a little primer on one of these things before we move on to the next video, just so you can think about these issues. To do this, we need to think of a correct rate for our sample to shear at. And the way you do this from the standards is you use this formula here. Vmax, or the speed, velocity, the maximum velocity of the loading ram, is equal to the height after consolidation times multiplied by the final strain of your sample over some factor times T100. And the thing that's interesting here is this height after consolidation. How are we going to find the height of this sample after consolidation? We can't measure it with a ruler or anything, because of two things: the optical distortion of the water within the sample, and obviously we can't put a ruler up next to it. Even if we could have a comparative scale, it would always be offset. It's not really very specific. So how, using the information we have available to us, can we come up with a height of the sample after consolidation? I'm going to leave you with that thought. Perhaps have a think of that before you go and watch the next video in the series, or consider that during the next lecture that Charlie's doing. And then we'll look at that next time. There is a right answer. Hope you can get it. If that's it for consolidation, we'll see you in the next one.